And so in order to solve this equation, we're going to need some approximations. And we're going to talk about the most basic approximation that there is, and that is called the one-electron wave approximation, or the one-electron orbital approximation. And here's the essence of that approximation. What we're going to do is we're going to take that wave function, and then we're going to assume that that wave function can be factored into a wave function for electron 1 times a wave function for electron 2. All right? So it's a one-electron wave. Each electron gets their own wave in this approximation. We're going to make a further approximation. And that is that we're going to give the functional form to electron 1 in the helium atom. We're going to give it a functional form that looks like that of an electron in hydrogen. We're going to give it the psi 100 wave function. Same thing for electron number 2. Or an alternate way to write that is 1s1 times 1s2, where this refers to electron 1, this refers to electron 2. And a more shorthand way is to write this as 1s2, 1s squared. Okay, so that's the approximation for helium. Let's just carry it out for lithium. Well, here's what the wave function would look like. Function of 9 variables, but we're going to give each electron its own wave function in this approximation. And again, we're going to say electron 1 has the 1s hydrogen wave function, electron 2 has the 1s hydrogen wave function, and electron 3 has the 2s hydrogen wave function. Another way to write that is 1s2, 2s. How about beryllium? 16. But we're going to use our approximation again. One electron has 1s, 1s, 2s, 2s. Way to write that, 1s2, 2s2. Hey, and we can keep going. And when I keep going, you go, oh, I've seen this before, right? You've written down the electron configurations for all of the atoms in the periodic table. Here they are. You know what those electron configurations were that you wrote down? Hey, they were just the shorthand notation for the one-electron wave function approximation to solve the Schrodinger equation. What you do notice is that when I got to boron here, I didn't give all 5 electrons the 1s hydrogen wave function. And when I got to carbon, I didn't give all 6 electrons the 1s hydrogen wave function. Why didn't I do that? Well, you already know that there's something called spin. All right? Okay. And you already know that in the 1s state, you can only put in 2 electrons. And one of those electrons has to be spin up and one has to be spin down. And the same thing for all of these other states. One has to be spin up and one has to be spin down. Here's the electron configuration here for neon. That electron configuration just being the shorthand notation for the wave function in the one-electron orbital approximation.